In the previous episode, we learned that electromagnetic waves are everywhere, from radio signals and Wi-Fi to visible light. But if they're all electromagnetic waves, what makes them different? The answer lies in two important properties: wavelength and frequency. Like ocean waves, electromagnetic waves repeat in a regular pattern. Notice the crests and troughs. This repeating nature allows us to measure waves in different ways. Wavelength, represented by the Greek letter lambda, is simply the distance between two identical points on a wave. Usually, we measure the distance from one peak to the next peak. Longer waves have larger wavelengths, while shorter waves have smaller wavelengths. This difference in wavelength gives each wave its own characteristics. Here we can compare two waves. The top wave has a long wavelength. The bottom wave has a much shorter wavelength. Notice that shorter wavelengths contain more cycles within the same distance. Frequency tells us how many wave cycles occur every second. The unit of frequency is Hertz, abbreviated as Hz. One Hertz means one cycle every second. 10 Hertz means 10 cycles every second. A low-frequency wave oscillates slowly. A high-frequency wave oscillates much faster. Higher frequency means more cycles occurring every second. In free space, electromagnetic waves travel at the speed of light. Approximately 300 million meters per second. This speed is represented by the symbol c. Wavelength and frequency are connected by one of the most important equations in electromagnetics. The speed of light equals frequency multiplied by wavelength. Since the speed of light remains constant, increasing one quantity causes the other to decrease. Frequency and wavelength are inversely related. This means that high-frequency waves have shorter wavelengths. and low-frequency waves have longer wavelengths. They move at the same speed, but their wavelengths are different. Radio waves have relatively low frequencies and long wavelengths. Wi-Fi operates at higher frequencies and shorter wavelengths. Visible light has even higher frequencies and extremely short wavelengths. Yet they are all electromagnetic waves. For example, many Wi-Fi systems operate at 2.4 GHz. Using the equation we just learned, the wavelength is approximately 12.5 centimeters. This explains why Wi-Fi antennas are often only a few centimeters long. Let's summarize. Wavelength measures distance. Frequency measures how many cycles occur every second. Electromagnetic waves travel at the speed of light. And as frequency increases, wavelength becomes shorter. In the next episode, we'll explore the electromagnetic spectrum and discover where radio waves, microwaves, visible light, and X-rays all fit together.